Hello, ladies and gentlemen. So now we are going to take a look at polynomial division, specifically long division. We've been talking about polynomials. We've been looking at how to do other operations with them, like add them, subtract them, and multiply them. Those are pretty simple, but now how in the world do we divide these things? So that's what we're going to take a look at today, and the procedure we're going to use here is long division. Long division is most useful in upper level math classes like pre-calculus, calculus. You use quite a lot of polynomial long division to determine things, but for the sake of our class, we're going to be using it to basically practice the operations and then later find factors. So we need that little foldable booklet you got from me, something to write with, of course, and a calculator would always be beneficial. So this is what your little booklet should look like. When you fold over the page, fold it over so that the problems are on the inside, and on the outside you can go ahead and write polynomial division, and then make sure that you label this one long division. We're going to make another one called synthetic division. Inside, you'll see some notes written for you already. Polynomial long division is essentially the same as long division of numbers. Now, it's been a long time since you had to long divide numbers, so we're going to take a minute and review that procedure. Oops, sorry, before we go ahead and start our long division today. So what is this useful for? It's useful to write improper polynomials, so division problems, as the sum of a polynomial and its remainder. So to determine remainders are useful in pre-calc and such for determining asymptotes on graphs, but for right now, we're just going to focus on getting the division down, okay? We can also use polynomial division to help you factor things completely, and this is where we will be going with this. So we need to be able to have this procedure of division under our belts because it's going to help us later on to actually find solutions. So let's review long division with numbers. You don't have this problem written in there, but I'd like you to write it in there. We remember way back when that we would take 172 divided by 3. Now this is before we operated a calculator, okay? We did the long division procedure. So how did we do that again? Well, we would ask ourselves, how many times does 3 go into or divide into the number 17? Or basically, 3 times what makes me a number really close to 17? Well, 3 times 5 would make me 15, right? So I'd place a 5 up here, and I'd multiply these two guys times each other. 3 times 5 makes 15, and then do you remember what you'd do when you'd line these numbers up under here? You'd subtract, right? You'd subtract them out. What is 17 minus 15? 2, right? All right. So then once we had a 2 down there, now you can't multiply 3 times anything to make it be a 2, but we drop down this other number here. And we'd say, what do I need to multiply 3 by to get me a number really close to 22? 3 times 7 is 21. Well, that's good. So we'd go ahead and put 7 up on top. We'd multiply the 7 times the 3, making 21. We'd subtract, making 1 my remainder. Now, for earlier elementary school grades, you'd go something like, hey, the R or remainder is 1. But later on, as soon as you started dealing with fractions and understanding what mixed numbers meant, you would understand this remainder as being 1 out of the 3 needed to make a whole group of 3. So you would write your answer as 57 and 1 remainder out of 3, or 57 and 1/3 would be that answer. So that was long division with numbers. Now how do we do this with polynomials? Well, I made a little box over here of the key questions I'm going to be saying to myself here, so that you can kind of keep track of that, but this is our first example. Now we need to take 2x squared minus 3x plus 1 and divide it by x plus 5. Notice they're polynomials. This is a trinomial, this is a binomial, he has 2 terms. We're going to divide them. We're going to do the same setup as long division. So on the inside, we're going to place this 2x squared minus 3x plus 1, and on the outside, we're going to divide it by the x plus 5. So when you first want to start a long division problem, you look at what's out in the outside here, and you look at that lead coefficient guy, or this lead. You look at this x, and you say, what do I multiply x by to get me as close as possible to 2x squared? X times what will turn into 2x squared? X times 2 and another x, right? X times 2x would become 2x squared. So now once I've decided what I need to multiply by for the x, I place them up here, and then I actually multiply. So I take 2x times this x, making 2x squared, but I also need to take the 2x times the 5, making me 10x, positive 10x. Now, just like long division, with numbers, you're going to draw a line and you're going to subtract these. Okay, this is the key part. 2x squared minus 2x squared would give you no x squared. So that's good. That means we did it right. What about negative 3x minus a positive 10x, or negative 3x minus 10x's? Negative 3 minus 10 more would be negative 13x. Notice we're subtracting there, not adding, okay? So now after I subtract, I go ahead and drop down the next number, which is a positive 1. I'm going to bring the sign and everything. And I do the same thing. What do I need to multiply this x by so he becomes negative 13x? What do I need to multiply x by to get negative 13x? Negative 13, right? So I'll place negative 13 up here, and once I place it up here, he gets multiplied by each of these two pieces out here. So negative 13 times x is negative 13x. Negative 13 times a 5, negative 13 times 5, let me check in my calculator before I tell you. Oh yeah, negative 65, okay? So that is negative 65. Now, once again, I'm going to subtract negative 13x minus negative 13. A minus and negative would become an add, right? And 1 minus a negative 65. Again, subtracting a negative becomes an add. So this is 66. So my remainder in this case is 66. Well, how do I write that remainder? How do I go ahead and find that remainder and write in with a fraction? Just like we did with the 1/3 before, this 66 is my remainder, and I write him as a quotient, or sorry, as a, yeah, I suppose as a fraction. It's a rational expression here, as a fraction with that x plus 5. So I'll say my answer is the 2x minus 13, and my remainder is 66, so plus 66 out of x plus 5, what I was dividing by. So plus 66 out of x plus 5. This is my final answer when I divide those two polynomials. That means if I really wanted to, I could go ahead and place an x plus 5 here and distribute this all out, guys, and then I would end up back with my original statement, the 2x squared minus 3x plus 1. Not that I'd want to do that with that fraction in there, guys, but I could. So remember, we're going to do this, what do I multiply by to get something else? We're going to multiply, we're going to line up and subtract, we're going to keep repeating that process, and we write our final quotient and a remainder as a fraction. So let's try a few more examples here. Here's example 2. You really get pretty good at it if you do them or try them, okay? So let's set it up division style here. So this is 2x squared plus 5x plus 3 on the inside and 2x minus 1 on the outside. So the way we get it started again, this 2x is the lead. That's what we want to look at. And we say, what do I need to multiply 2x by to turn him into 2x squared? We need to multiply him by another x, right? So when I do that now I need to distribute to both pieces. X times 2x is 2x squared. X times negative 1 is negative 1x. Subtracting, okay, 2x squared minus 2x, nothing. 5x minus negative 1. Minus a negative is like an add, so 5x plus 1 is really 6x's. So I'm going to drop down the next guy. After I subtract, I drop down the next term, and I do the same thing. 2x, what do I need to multiply him by to turn him into 6x? What would I need to multiply him by? 3, right? So plus 3 right here. 3 times 2x is 6x. That means I did it right. And then 3 times negative 1 makes negative 3. I'm going to subtract, okay? Now, go ahead and subtract 6x minus 6x is no x's. 3 minus negative 3 is like an add, so this gives me a remainder of 6. So my remainder of 6 gets added up here, plus 6 over 2x minus 1. So my quotient, or my final answer, is x plus 3 plus the remainder fraction 6 over x minus 1, okay? The remainder is 6, and I make it be a fraction with what I was multiplying by. All right, let's try another one. Here you go, example 3. So I have x to the fourth plus 4x to the third plus x minus 1 divided by x squared plus 3x minus 5. There's a lot more terms involved here. Don't worry, okay? The key thing to keep in mind is that notice this first polynomial right here. There's something we should check before we actually set him into the division setup. Notice the degree here is 4. That means he starts with 4 as the highest power. Then it goes to 3. What should come after an x to the third? An x squared, right? There is no x squared. We need to remember that when we set up our division, that we have x to the fourth plus 4x to the third plus 0x squared. We need to make that 0 be written in there. Even though he's not a part of the problem, he should be there. X squared should be there, but there are 0 of them, and that's why we don't see them. Okay, plus the x minus the 1. And now over here, we're going to place x squared plus 3x minus 5. Now remember, I made a little bubble over here. If a term is missing, write 0 as a placeholder. That's going to be a rule for us anytime we divide, okay? So again, I'm going to look at this lead. X squared, what do I need to multiply x squared by to make x to the fourth? Oh, I need to multiply him by another x squared. So now that I placed x squared up here, I need to multiply x squared by all 3 of these terms and line them up. X squared times x squared is x to the fourth. X squared times 3x makes 3x to the third. That's a positive. X squared times negative 5 makes negative 5x squared. So I'm going to go ahead and subtract now. X to the fourth minus x to the fourth, none. 4x to the third minus 3x to the third makes 1x to the third. 0 minus negative 5, minus a negative is like an add, so plus 5x squared. And I'm done subtracting now. So just like the last one, we're going to go ahead and drop down the next term. So now once again, we go back to our lead and we say, okay, before we can do this again, what do I need to multiply this x squared by to turn him into 1x to the third? We need to multiply him by another 1x, right? 1x. So 1x gets multiplied by each 3 of these trinomial pieces out here. So 1x times x squared would be 1x to the third. The 1x here times the 3x there would be 3x squared. The 1x times the negative 5 would be negative 5x. And we're going to go ahead and subtract again. 1x to the third minus 1x to the third, none. 5x squared minus 3x squared is 2x squared. 1x minus negative 5. Oops, I heard minus a negative. That's like an add. So 5x plus an x would make 6x's. Okay, I'm going to drop down the next term, negative 1. This is why they call it long division, you guys. All right, last time. Here we go. What do I need to multiply x squared by to make 2x squared? Just the number 2. Now if I multiply them by the number 2, 2 times x squared is 2x squared. 2 times 3x is 6x, positive. 2 times negative 5 is negative 10. Now I'm going to subtract. 2x squared minus 2x squared, none. 6x minus 6x, none. Negative 1 minus negative 10, there's 2 minuses again. That will be 9. So my remainder is 9. So my final answer is x squared plus 1x plus 2 plus my remainder of 9 over what I was dividing by, x squared plus 3x minus 5. This is how I would write the answer or the quotient for that division problem. All right, last one. Here we go. You can do this. Let's make sure before we set this up, now that you've seen the little trick with zeros, are we missing any terms in here? Starts with an x to the third. After that should come x squared, then an x to the 1, which we have, and then no x's at all. Nice. So it's all there. We don't need a 0 here, guys. So I'm going to place the x to the third plus x squared minus 8x minus 12 in here, and then the x minus 3 goes out here. What do I need to multiply the x by to turn them into x to the third? X squared. Now I'm going to distribute. X squared times x is x to the third. X squared times negative 3 is negative 3x squared. Subtract. X to the third minus x to the third, nothing. X squared minus a negative again is like an add. So 4x squared. And I'm going to go ahead and drop down the next. That is negative 8x coming down. Now I'm going to ask myself the same question. What do I need to multiply this x by to turn them into 4x squared, or to basically cancel out the 4x squared? Well, I need to multiply them by a 4 and an x. Positive. I like it. So here we go, distributing now the 4x that I placed up here. So 4x times x is 4x squared. 4x times negative 3 is negative 12x. Subtracting. 4x squared minus 4x squared, nothing. Negative 8 minus negative 12 is 4. Again, remember I was subtracting a negative there. When you subtract a negative, it's like adding. Drop down the negative 12. One last time. I need to multiply this x by somebody to turn him into a 4x. Well, I would just need to multiply him by the number 4. So 4 times x turns into 4x. 4 times negative 3 becomes negative 12. I subtract. 4x minus 4x is nothing. Negative 12 minus a negative 12, that's like adding negative 12 plus 12 would be 0. Yay! I got a remainder of 0. What does that mean? My final answer is just then x squared plus 4x plus 4, no remainder with a fraction here. But that means that x minus 3 is a factor. He divides out evenly. He was multiplied by something to make something nice, something polynomial style here to make this original expression here. So that means x minus 3 times x squared plus 4x plus 4 was in fact what was multiplied to make my original statement here in this circle. So understanding that when you get a 0 remainder, it means that the x minus 3 was a part of the factoring. That's going to be huge for us later on. X minus 3 is a factor because his remainder is 0. So, ladies and gentlemen, I want to thank you for taking good notes on long division. There's a reason it's called long division. It takes a little time, and it does take a lot of thinking and careful subtraction. So be careful on your work and on your practice, okay? Ladies and gentlemen, thank you for taking good notes. Kincaid out.